So the first one is it's called as the center tapped transformer. This is how the circuit looks like. Unlike traditional transformer, so what you see here is in a center tap transformer, the middle terminal. So remember that the traditional transformers will be looks like this. So you have primary and you're going to have a secondary, pretty much, correct? That's a traditional transformer we saw in the last class. But in a center tapped transformer, the number of turns on the secondary side will split into half, and there is going to be one lead coming out of the secondary side of it. So the center tap will usually have 3 leads on the secondary side. So the reason why it's a center tap is the voltage will be split exactly into half. So for example, if the entire secondary voltage is, let's say for example, the entire secondary voltage is, let's say 60 volts, half of that voltage will be available to the center tap, and the rest of the half will be from the center tap to the another side of the transformer. So that entire secondary voltage will be split into half on the secondary side. That's why you can observe right here in this figure, it says what? V secondary divided by 2. That's one difference. Another difference is you can observe the signal shape right here versus signal shape right here. What happened to the signal itself? It's inverted. So that means it's inverted by what is the phase of that inversion? The signal was flipped by 180 degrees. These are the two things a center tap transformer will do it. So its voltage on the secondary side will be half of it on the top portion of the secondary side of the transformer. That's why you see right here it says V secondary over 2, and the rest of the half voltage will be available from the center to the bottom side of the transformer. That's from the voltage perspective. That's half and half we are talking about. Just one half of the signal.
Well, when one's negative, the other one's positive. One person negative, the other one's positive. One person positive, the other one's negative.
Again, this is a phase shift. Of course, for AC signals, there is no such thing as a positive or negative as a magnitude. We only talk about their phase shifts. Of course, that implies, yes, one negative voltage. But if you remember, you don't really see negative voltage on an oscilloscope, correct? It either shows you peak or peak to peak or RMS. There is no voltage that you will see like negative 3 volts peak to peak. But it's our understanding that if you see negative in front of an AC signal, that's pretty much the signal is inverted in its phase by 180 degrees. So that negative is only indicating that for AC signals, it is a phase inversion. For DC, yes, DC signals could be negative or positive. But for AC, if you put a negative in the front, that only implies that it's a phase inverted signal.
So if you flip the diode, you get negative voltage.
Yes, that's possible. Yep. Exactly like an half-wave rectifier. But remember that this phase is being caused by not the diodes, correct? This phase inversion is being done by what? The transformer itself. So diodes basically not do anything. Diodes cannot flip out any phase of the signal, right? Here the phase inversion is purely caused by the center tap transformer. So this is the circuit of, so after the transformer, You see that center tap transformer requires 2 diodes. Right? Observe that both diodes are facing in the same direction too. And then both are meeting together. And then finally you have your load resistor. So that's where your peak output voltage is. So this is where our output voltage is. That's where we are collecting it. Again, the signal shape we are expecting here is what? What is the signal shape we are expecting here? So it's pretty much like it's a full wave. And again, the frequency should be double the whatever the input signal frequency is. For example, the line frequency, if it's 60 hertz, then you will see is, this is a very important factor in full wave rectifiers, and you will use these values in the filtering stages as well. That's why you need to be really careful to check whether the given rectifier is a half wave or a full wave. But do not confuse that half wave doesn't mean the frequency will be half. Half wave only implying that half of the signal will be transferred over one cycle, but frequency remains the same. For half wave, if you feed in 60, you will get 60. If you feed in 120, you will get 120. But full wave, frequency will double. If you feed in 1000 hertz, you will get 2000 hertz, and so on.
So if you're feeding in 60 hertz, 60 volts, peak to peak, you're getting out 60 volts positive at 120 hertz.
Not necessarily 60 volts. The voltage could be depending upon, for example, if you feed in 60 volts, you're definitely not going to get 60 volts right here, because you have some diodes in there. And of course, this is that means you're going to step it down. Remember, you're going to step it down, but each diode is only receiving what? Half of the secondary. So there are some things we need to look at. So if you take a look at on your formula sheet, what is the formula for V peak out? Again, keep your formula sheet handy. What is the formula for V peak out for center tapped?
2 times voltage peak out divided by 5.
Not average.
Oh, peak out?
Yep.
Okay. Voltage peak over the secondary divided by 2 minus 0.7, which is the diode drop.
So this is the formula, correct?
Yes.
Is that right? So as you can see, you're only taking half of the secondary, correct? Remember in the last class we talked about how to deal with transformers with a turns ratio, right? So that remains the same because this is still transformer. But observe, each diode is only receiving what? Half of the secondary. As you can see that each diode right here, it's only 1/2 of the secondary, not the entire secondary. So as you can see that V peak out formula, it's V peak secondary over 2, which is 1/2 of whatever the secondary is, subtracted with 0.7.
This case would be 30 divided by 2. This case. So you're saying the 60 hertz come in, it comes out as 30 hertz, double the frequency? No. 60 hertz comes in, 120 hertz comes out. We're talking about voltage, 60 volts. That's right. Voltage should be 30.
Again, we will do some examples on calculation of voltages. Again, we don't know what's turns ratio right here on the transformer. Correct? Again, if there is no turns ratio here to tell what the secondary is. So
There's no ratio. Do you not assume 1 to 1?
not necessarily, this is just a figure that's showing you the circuit. So, but if you say, just for sake of discussion, if you say 1 to 1, what does that mean? So that means the total secondary would be what?
30. Oh, 60. Oh.
The total secondary will be 60. 1/2 will be 30. So in this example, it's basically 30 minus 0.7.
Divided by 2 minus 0.7.
Yeah, we already divided by 2 right here, right? So 60 becomes That's V peak secondary. The total secondary is 60. You half of it, that would be 30 minus 0.7. So that would be 29.3. That's what the peak voltage is, 29.3. But the frequency would be what? 120. So the voltage is 29.3, but the frequency is 120 hertz.
I thought you dropped 0.7 on each side.
Yeah, that's a very good point. So why can't we do 0.7 on each one? Remember, there are two diodes, right? So we will talk about the operation soon. We haven't talked about how this operates yet. So, but this one basically shows the circuit only. So this only shows you the circuit diagram of the center tapped, right? So let's take a look at how this is actually operates in terms of so during the positive half cycle of the input signal, again input signal is coming, that's pretty much a sine wave. So if you look at positive half cycle, which diode will be forward bias? Because remember that this is a center tap transformer, meaning that the top of the diode will get the same signal as whatever the input signal shape is, but the bottom diode will get what? It's going to get an out of phase signal, meaning that when the input signal is positive, this one will be positive, but this one will be negative. So when the positive voltage feeding through this diode, that diode will be forward bias. But at the same time, this diode is being fed the negative cycle. So that means this is going to be forward bias, but the bottom half of the diode will be, it's going to be reverse bias, because the center tap transformer is performing that phase shift. So when the top diode getting the positive cycle, the bottom diode gets the negative cycle, correct? So the top diode will be forward bias. That pretty much allows the current, right? So what you will get is the same positive half cycle that we're talking about, of course, minus 0.7. But you can think of at any given time, does both diodes are become forward bias? No. That's why the formula has only one single 0.7, not 2 0.7s.
This is the center tap, right?
Yes, this is the center tap. So when the input signal gets negative, when the input gets negative, the top diode will get the same negative, but the bottom will get the positive. So that means this one would be reverse bias, but this one would be forward bias. So again, the type of signal forward biasing the diode is the positive cycle. So the next half would be positive as well. Yeah, we are talking about the shape. So how the full wave rectifier shape is going to be like that. Because the phase shift. The phase was shifted by the transformer itself. Correct?
Was it shifted by the center tap, right?
Yes, the phase was shifted by the center tap. As you can see that these two signals are having the same phase.
So can you flip the diode so you don't have cancel each other out?
If you flip at least one, then you're not going to get anything. Then you're going to get pretty much the same way. How does that get? So are you saying that reverse one diode?
Was the previous picture both the diodes were forward biased with the previous slide?
The previous slide, it just shows the circuit. That's it. It doesn't go into the operation. It's the same circuit pretty much. If that's what.
Okay, so you're saying they have to be flipped. The diodes have to be
This is just a given circuit of center tapped, and this is how a center tapped full wave looks like. The diodes both will face in the same direction.
the diodes. Well, it looks to me like two forward-facing diodes.
Yes,
So the one you went for the other one,
and they are forward facing as well.
also forward-facing, but you have them.
Because here we are talking about the operation. That's why it's being shown like one is in green color, one is in like red color like that.
I was thinking that there were two.
So this is the direction of the diodes will be, both are facing towards that way.
And the first
And that's how it will be phased.
top diode is second half of the phase, bottom diode. Because the bottom part at that point has gone positive.
So the signal right here, remember center tabbed, one half of the signal will be in the same phase shift as the original signal. So if the original signal is like this, again, we are not talking about how much voltage here. We are talking about the shape of the signal only. We're not concerning about how much voltage we are talking about here. So for example, if this is my input signal, so this is exactly what my input signal is. Again, that's with respect to the phases of the signal. Yeah, this one is only during the positive half cycle, this particular slide. So the signal right here at the bottom will be in the opposite phase shift, meaning that when the top diode gets positive cycle, the bottom diode gets negative cycle. When this gets negative, this gets, that means when this forward bias, this will reverse bias. When this will reverse bias, this will forward bias. Reason for what?
It's not. If you do one, it looks like this.
Remember, this is a full wave rectifier. How does the output signal of a full wave rectifier looks like? Is it the same as in half wave? So you got a different circuit, right? So the signal outcome of the signal shape is definitely going to be something like this, right? So to achieve that, this is one type of circuit. If you take away one diode altogether, then that would be what? So it's not going to be full wave.
Because you're using the full sine wave, both halves of it.
The signal comes out of it looks like this. What rectifier this would be? This circuit is responsible for a full wave. So why we are getting full wave? That's the operation we're just talking about. Again, why only this circuit? There are a lot of circuits available. This is just, we are talking about one circuit. Right? So this is a full wave rectifier only. Right? This is, again, the terminology might be different. So this one will be basically occur during the duration of one cycle of the input signal. But this is not a full wave. It's not a full wave. Right? Again, depending upon what your definition of full wave means. So if you think full wave is this, you can tell that's not a full wave. If this is what you are thinking as a, okay, this is what a full wave is, as you can see, this is not a full wave. So this is not a full wave. The name full wave means the signal will be available for entire 360 degrees of the input cycle. Now, that's two repetitions. Again, what is your definition of cycle? So it's a repetition. But full wave rectifier doesn't mean the signal is a full wave. It only means the current will be there for entire 360 degrees on the load resistor.
It's using the full wave of the sine wave.
Yes.
Half wave, it's only using half of the sine wave. Or it's only using half the positive part. On the full wave, it's using the full wave of the sine wave. Positive and negative. More current. Have a more stable mode.
Again, what would be the advantage we will talk about later on. If that's what you are looking for, that's too soon for right now. Yeah, why it makes the advantage in terms of using it as a full wave, we haven't done that portion yet. This is only shows you what the slide title is, operation. So I think you guys are jumping ahead and look for problems and how to solve it, how to use equations. So this is only shows you the operation. So it's not going to show all the problems, examples, why this is an advantage over the half wave. All will comes down the line. So, but this is only shows you the just operation of how this circuit will provide you two voltages or two exactly positive cycles, one after the other, pretty much. All right, why this thing is... All right, so let me try a different way. Wow. All right, all right. So this is on the negative half cycle. So as you can see in the negative half cycle, this diode will get some negative orientation. So that means again the phase of the signal is when this gets negative, the other one would be negative as well. But this bottom diode, remember this side will be phase shifted. So it will getting the positive half cycle. So when this gets negative, this gets, so that means according to the orientation of diode, this diode will be, and this diode will be forward bias, which is opposite to the previous explanation. So as you can see that the signal shape is positive. That's why the second portion will be positive as well. So the phase is shifted by the transformer itself, not the diode. So diode is simply either forward biasing or reverse biasing. Right? So that's why the second, during the negative half cycle as well, you are getting the positive cycle, positive half cycle. Because the phase was shifted and this diode is being forward biased. And both together will give you this sort of waveform. Again, this is only explanation to how come we get this waveform in a full wave rectifier. Right? So that's pretty much why if you take away one diode altogether, then it's not going to be a full wave rectifier. It's only a half wave rectifier. If you take away one diode, it's the same as whether you use a center tap or don't use a center tap, it doesn't matter. You still get a half wave. But if you flip both diodes backwards, both of them, not just one of them, then what do you think will happen? So you will get, if you flip both of them, so this is what you will get. So you will still get full wave rectifier. Still get a full wave rectifier. But the voltage, effective DC voltage would be negative. But that's only when you flip both of them, not just one of them.
So rectifier allows current one direction.
Yes, yeah.
Can't change direction.
After the rectifier, yeah, rectifier is only for one direction of current. That's why when you're doing AC to DC, DC is only one direction. So rectifier means it's going to allow only one direction. Whether it is like this, that's only negative. When you say this, that's only positive, not both, right? So this one pretty much is in terms of what a center tap transformer is and how can we make use of that transformer in order to deal with the full wave rectifier. Again, the load will have current throughout the duration of the entire 360 degrees, whereas half wave is the load will have a current only during the positive cycle, but this one is like 0 amps, so the load will not get any current during that time, correct? Because the voltage is 0. But for full wave, it's not like that. The current is available towards the load resistor for the entire duration. So that being said, full wave rectifier utilizes in terms of efficiency point of view, because here half of the power will be lost, correct? Even though the signal is available at the input, for half wave, the load will not get anything, correct? So you're losing some power when you use a half wave rectifier. So some of the power coming from the source was not properly efficiently used. But whereas a full wave, that power is, because that signal is now available when you use a full wave, so you are efficiently using the incoming signal power when you use a full wave rectifier. So that's the one advantage is in terms of the power delivery to the load. So that's from the load perspective. So the efficiency standpoint, that's another reason why full wave rectifier is preferred over half wave. So power is available to the load because the circuit operates for entire 360 degrees of the input cycle. For half wave, it's only 180 degrees. But any load means what you are supplying power to. So in here, the resistor is being the load. But at any given time, only one diode is forward bias. That's why if you take a look at your formula for V peak rectified, the formula only shows you negative 0.7, correct?
Yes.
There is no 1.4 from the formula. At any given time, it's only one diode. That's why it is, the formula is the peak output voltage. Again, everything should be in peaks. Is 1/2 of the secondary voltage minus 0.7. Because remember that each diode is only getting 1/2 of the secondary, correct? And you take away 1.7 value because at any given time, only one diode you need to exceed the barrier voltage. Another one is already reverse bias. So that's the V peak out. Is the output voltage, again, peak value of the output voltage. Again, this is not average voltage. This is what, for example, if you're drawing full wave, this is the peak value of the full wave. So that being said, is pretty much just this portion, how much that value is. That's that. That's what it means, right? Peak. Peak is the highest point in the signal. So Whereas the PIV rating, remember PIV, which is for, it's the peak inverse voltage. What it implying? So what is peak inverse voltage? What is the purpose of a peak inverse voltage? What it shows us? So it's the reverse bias voltage. The diodes can safely operate without damaging the diode. So how the safe voltage for better operation for the diode in the reverse bias. So it's twice the whatever the peak output voltage is plus 0.7. So that's the formula for a full wave, but that too it's a center tap transformer. So this one is for a full wave with a center tap transformer. That's the PIV rating for the rectifier itself. So whatever this voltage is, the diode should capable of handling that in the reverse bias. So that's for safe operation. So this is pretty much what a full wave is in terms of the formulas that are used to do it, to calculate the full wave rectifier. All right, so we will take a break and we will proceed to how to use these formulas. Again, in the lab, we don't build a center tap full wave rectifier because this requires a center tap transformer. So we have it in here, but since we are using it on the Elvis, whenever we build the full wave rectifier, we go with the bridge rectifier. Bridge does not require any transformer at all. So we can use a bridge rectifier. So next class, you will do a lab on the full wave rectifier. Today we will be doing the half wave rectifier only. So there you will see a bridge rectifier, not a center tap transformer. So, all right, so we'll meet at 9:30 to continue with some examples on this type of rectifier to see how to deal with calculation of output voltages and PIV ratings. And after that, we will do the bridge rectifier. That's the last full wave rectifier type.